Whenever we think of graphs, we tend to think of them as arising from algebraic equations. However, this has not always been the case. In fact, for most of the history of mathematics, mathematics was synonymous with geometry. There was really no other brand. There certainly wasn't any calculus. There wasn't any algebra. Algebra didn't really take hold in the form that we know it until the 1500s. From Euclid's time, which was roughly 300 BC, up until relatively recently in the history of mathematics, geometry was the way mathematics was thought of. And so graphs didn't arise from algebraic equations. In fact, algebraic equations didn't even exist. Let me give you an idea of how Euclid would have described a particular curve that I think you'll find familiar, although the form in which he thought of it, you probably will not. Euclid was very interested in a curve that was described as follows. Begin with a straight line and a point that is not on that line. And consider the set of all points that are as far from the line as they are from this fixed point. Well, one such point would be this one, right? The one that is right in the middle, right between the point and the line. But there are many other points that are equidistant from the point and the line. For instance, let's just draw several of them, right? So see how we're making sure that the segment between G and J is the same length as the segment between J and L. And we're going to consider all such points. Perhaps you can see what shape this might be tracing out. Of course, we're going to have some on the other side, right? It's going to be a lot of symmetry involved here, right? So what shape is this? If I draw it quickly, can you kind of follow the set of points being traced out? Well, just in case you can't, I have drawn it for you. Here it is. And it's what you know as the parabola. But the description that I just gave to you is the one that Euclid would have known. And while you probably think of a parabola as the graph of a quadratic equation, in Euclid's time, and up until relatively recently, no such description was possible because algebraic equations didn't exist. It wasn't until the time of Rene Descartes, roughly 1620-ish, whenever the idea of graphs of algebraic equations were even possible. He was the one who invented the idea. In fact, what he did, this is a great story, I think. He was a rather sickly individual, and he spent a lot of time in bed. And as the story goes, he was laying in bed one day, looking up at the ceiling, and on the ceiling was a pattern of squares, a grid of squares, like you'll see on many ceilings today. Perhaps square tiles, not sure, but on his ceiling, he saw a fly. And it occurred to him that he would be able to describe the location of that fly by telling somebody how many squares over and how many squares up to go from a particular fixed point in order to find where the fly was sitting. And it was in that stroke of genius that the idea of coordinate geometry was born. The idea of taking the plane and putting numbers on a couple of axes and using those numbers to describe points of the plane. So let me take you to the whiteboard and let's see how Descartes' idea turned Euclid's idea of a parabola into the idea of a parabola that we consider. So he took Euclid's line, point off the line, and the set of points that are equidistant from the point and the line, and he put those around a set of coordinates. So for convenience, I'm going to let this point be the origin. I'm going to let this be y equals 1. We'll think of that as the y-axis. This is the x-axis. And we'll think of this line lying here at -1. And let's describe a point that's on this parabola in the same way that, that Descartes would have described the location of the fly. So he would have said, well, let's go over so many units, and we'll say that he went over x units, and let's go up y units, and we'll describe the location of the fly as the point x comma y. So we're going to describe the location of this point on the parabola as x comma y. Well, what do we know about x comma y? We know that it's the same distance from this line. So y is just describing from here to there, right? But the distance between the point and the line is the same as the distance between the point and this number 1. I guess 1 would have coordinates, so the x-coordinate of 1 is 0, the y-coordinate is 1. And so what does that mean? Well, I'm just going to bring a line over here to make a little right triangle. Right, so let's see, what are the distances here? Well, let's see, so this leg is length x. This leg is length, well, let's see, I guess y minus 1, isn't it? And so we have that this distance squared is x squared plus y minus 1 squared, right? But we know, because it's the way it was defined, that distance right here is the same as this distance right here. And this distance is what? Y plus 1 unit. Well, if this is the square of our hypotenuse here, then that's going to be equal to, I guess, the square of this distance. So y plus 1 quantity squared. And there we have an algebraic equation which describes the parabola. We could simplify this. In fact, whenever we do, I think you can see that our y squareds are going to go away. We're going to have a y term that appears whenever I carry out this the squaring of this binomial. We're going to have a y term there. So we're going to have a y term, no y squareds, and we're going to have x squared terms. We're going to wind up with a quadratic equation whenever we solve this, which is the way you and I tend to think of a parabola today. But again, it was Descartes' brilliance that allowed us to make that distinction. And in fact, it was at that point, mathematicians had a new way of studying graphs, and it was relatively recently after that. This happened at around 1620, 1630. Well, Newton was born in 1642. In fact, Newton was born just 8 years before Descartes died. So it was just that quick after the invention of coordinate geometry that there was some human on the planet who was able to invent calculus. I'll bet somebody would have invented calculus many years earlier had coordinate geometry been a thing much earlier. Just a guess. So just for kicks here, how would a circle be described? So in Euclid's time, a circle would have been described as the set of all points equidistant from a given point. After Descartes, we could describe a point xy on the circle as, well, we're going to use algebra to describe exactly that same definition. So if we say that every point on the circle is exactly 3 units away from this center point, then I'm going to draw a little triangle here. And again, I'm going to read off the Pythagorean theorem. This is our x coordinate. This is our y coordinate. This says exactly that x squared plus y squared is 3 squared. And so now we have this algebraic equation to describe this set of points rather than that verbal description of all points equidistant from some central point. Okay. Let's suppose for just a moment, though, that whenever Rene Descartes was lying in bed, the ornaments on his wall looked different. Maybe they weren't tile-shaped. Maybe instead he had a spider web design on his ceiling. What might he have proposed about the location of a fly then? Let's say that the fly was right here. It might have been more natural for him to identify perhaps one of these rays as being special, and the angle between that fixed ray and the ray on which the fly was located. So he might have described that as some angle. And then he might have said, well, along that ray, go out so many units. So in this case, I have perhaps 2 units. And so instead of describing it in terms of an x coordinate and a y coordinate, he might have described it in terms of some radius and some angle, some distance from a central point together with some angle that that this ray makes with some fixed ray. And so, right, so this would have been, if this, let's say this angle is, I don't know, how about maybe pi over 6 radians, maybe pi over 8 radians. So we might have described this point as 2 comma pi over, we'll use pi over 8, right? Not an x coordinate and a y coordinate, but a distance from center and an angle. So in this coordinate system, what would a circle of radius 3 look like algebraically? Right? In rectangular system, an equation of a circle centered at the origin of radius 3 was x squared plus y squared equals 9. But now we're using completely different coordinates, right? We're using how far from center and what angle is being made. Well, turns out the angle that's being made is really unimportant, right? No matter what point I'm looking at on my circle, the truth about that point is it is 3 units away from the center. That's true regardless of the angle. And so it turns out that the equation r equals 3 completely determines the points that are on this circle, right? That's the equation which captures the truth about points on a circle in this coordinate system. R is always 3. We're always 3 units from center, regardless of the angle. So we wind up in this coordinate system. Circles have a very, very simple equation, at least circles centered at the origin do. Okay, so let's consider some relationships between the two coordinate systems, what we would refer to as the rectangular coordinate system, right? The one that Descartes invented, the one he saw whenever he was looking at his ceiling, and this polar coordinate system. Well, I'm just taking an arbitrary point here. In the rectangular system, I would describe that point with the coordinates x and y. In the polar coordinate system, I'm going to describe that point with the coordinates r and theta. Incidentally, whenever we have two coordinates describing a point in polar coordinates, we always write the distance from center first, and we always write the angle second. Just like in the rectangular system, we always expect our first coordinate to be coming from the horizontal axis, and the second one coming from the vertical. Anyway, so if I have a point that can be described xy in rectangular form or r theta in polar form, here's a picture that establishes the relationships. So certainly x squared plus y squared is going to be r squared, right? If I divide x by r, what I'm going to get is the cosine of my angle, right? So if x divided by r is the cosine, then x is going to be r times the cosine. Similarly, y is going to be r times the sine of the angle. And if I divide the coordinates y by x, then I'm going to get the tangent of my angle. So these four equations help us to translate between the two coordinate systems. So, for example, right, if I had a point x comma y in the rectangular system that was 3 comma 4, well, let's see. So there's my x, there's my y. So I know if I square x, square y, and add them together, I'm going to get the square of r. And so 3 squared plus 4 squared is 25. So r must be 5. All right, and what else? Well, let's see. I need to know my angle as well. And since I know what x and y are, I could divide y by x, so divide 4 by 3. That's going to give me the tangent of my angle. And so I can get the angle by looking at the arctangent of 4/3, which is roughly 0.927, right? And so in polar form, 3 comma 4 in rectangular coordinates is going to be written as 5 comma 0.927, roughly. Okay, or let's consider r comma theta being negative 5 pi over 3. What do I mean by negative 5? I've just said that this first coordinate describes the distance from center. Well, negative 5, that's a negative number. That's not a distance. Well, here's how we interpret that. So what I've drawn here is the point 5 comma pi over 3, right? So I'll go pi over 3 radians from my fixed, we'll call it the positive x-axis. And so if I go 5 units out along this ray, I'm going to have the point 5 comma pi over 3. But if I want negative 5 comma pi over 3, then what I'm going to do is go backwards along this ray. Instead of going from the pole out 5 units on this ray, I'm going to go backwards 5 units. Right? And so this point down here, that's going to be what I call negative 5 pi over 3. So that's what I mean by this. Now, can we find what that would be in rectangular coordinates? Well, sure. That's actually pretty straightforward. I know that my x-coordinate is going to be r times cosine theta. Well, r is negative 5, cosine, and theta is pi over 3. So I wind up with, let's see, cosine of pi over 3 is a half. So x is going to turn out to be about negative 2.5. Similarly, y is going to be, well, let's see, sine of pi over 3 is square root of 3 over 2. And so I'm going to wind up with negative 2.5 times the square root of 3. So, so in rectangular coordinates, I would write that xy is equal to negative 2.5 and negative 2.5 times the square root of 3. So these 2 points describe exactly, or these two descriptions describe exactly the same point down here. This one does it in polar form. This one does it in rectangular form. All right. How would I convert the equation r equals 3 cosine theta, so that would be an equation in polar coordinates, to an equation in rectangular coordinates? Well, we've just seen how to convert points from polar to rectangular and from rectangular to polar. How would we convert an equation from polar form to rectangular form? Okay, well, let's just look. Here are the equations that I might use in order to do the job. And I'm going to start with r equals 3 cosine theta. And let's see, what would you do? In fact, why don't you pause the video for just a moment and see if you can rewrite this entirely in terms of x's and y's. Okay, so how did you do? There are several ways we could proceed. Here's what I did. I started by noticing that x is equal to r times cosine theta, so I could right away replace cosine theta with x divided by r. And so that's what I'm going to do first. And if I multiply at this point, if I multiply both sides by r, then I'm going to have r squared equals 3x. And r squared is x squared plus y squared. So there we have it. That's an algebraic equation in terms of x's and y's entirely that describes exactly the same curve that r equals 3 cosine theta would be describing in polar coordinates. I've actually gone a little bit further. Perhaps you recognize that since I have an x squared and a y squared, and they both have the same coefficient, 1, that I might be able to write this in a more clever form that would allow me to graph this equation pretty quickly. What I'm going to do is subtract 3x from both sides, and then over here I'm going to complete the square. So I'm going to take half of the coefficient of the x term and square it and add. Of course, whenever I add it to the left side, I'm going to have to add it to the right side also. And so what I've got is, so I completed the square over here, so I can write this as a perfect square, x minus 3/2 quantity squared. This should be a plus. And I wrote this as y minus 0 quantity squared, just to put it in a form that you may be familiar with. This is exactly the standard form for the equation of a circle. Centered where? Well, centered at 3/2, comma 0, and with radius 3/2. And so the graph of this would look like this, right? So center is at 3/2, comma 0. The radius is 3/2, and so there's my circle that describes this equation. How do you think I could graph this equation without having converted it into a form that I'm more familiar with? Well, I have a method for that, and I'm going to show it to you. What I typically do is I use my knowledge of what this curve is going to look like in rectangular form, right? I know what 3 cosine theta looks like if I'm graphing it in rectangular form, and I'm going to use that information to inform how I'm going to graph it, in polar form. So here we go. I'm going to pick a starting point, and this looks like a pretty good one. what this tells me is that, right, so this is my theta axis right here. What this tells me is that whenever theta is 0, r is 3. Well, in my sketch over here, what that says is, let's see, whenever theta is 0, so that would be my positive x-axis, wouldn't it? And when theta is 0, that is the ray that I'm looking at. And I'm going to go out 3 units on that, right? So 2, 3 units on that. So that's going to be a point that's on my graph. And then I'm going to start increasing my values of theta until I get to pi over 2. In fact, let me draw, I'm just going to draw some rays along here that indicate theta increasing. Right? And so what's happening is, as my thetas increase to pi over 2, where's pi over 2? Pi over 2 is going to be the positive y-axis here. As theta increases to pi over 2, my r's are steadily decreasing to 0. So I'm starting at 3. I'm going to wind up along this line. I'm going to be at the pole. We don't call this the origin anymore in the polar coordinate system. We call it the pole. And so my thetas are decreasing very slowly at first, right? This is a slope of 0, so my r's aren't changing very much at first. But then they're going to change a little more rapidly, and a little more rapidly, a little more rapidly, until by the time I get to theta equals 0, I'm at the pole. And notice too, when I'm at the pole, the ray, so this is going to be the ray described by theta equals pi over 2, that ray is going to be tangent to the graph of my equation every time. So I want to make sure that I put that information into my graph. So I'm going to just remind myself of that by drawing a little bit straight up and down, and then I'll kind of connect these dots. I'm missing them here. There, I hit them now. All right. So my theta values are increasing to pi over 2, but my r's, the distance out from the origin, is decreasing until I get down to a distance of 0. Between pi over 2 and pi, oh, look at this, my radii are negative, right? So I could draw my theta lines this way, but because my r values are negative, I'm not going to be sketching in this section. I'm going to be sketching, remember what happens with negative values. So whenever I'm at theta is this angle, I'm going to be sketching along this line, and so on. So I might as well draw my lines out this way. And what's happening? So my r values are showing that I'm getting further away from the pole, but I'm getting further away in a negative way. So keep that tangency here and start increasing the values of r until I'm 3 units away from the pole. Let's see how my r values are increasing as I move along, until at this point they're at 3. And there it is. I've got a complete circle. And if I continued this, if I continued graphing from pi to 3 pi over 2, well, let's see, my distance from the pole is going to go back to 0 again. Instead of graphing in this region, I'm going to be graphing in the opposite of those lines, right? So I'm going to be plotting along these rays, and I'm just going to retrace right back over the part of the graph up here that I've already drawn. And from 3 pi over 2 to 2 pi, I would do the same thing. So actually, as theta goes from 0 to 2 pi, this circle gets traced twice. And that's how I can sketch the graph of a polar equation directly. Sketch it in rectangular form, and then use that to inform us of what the polar form is going to look like. Let's try that with another equation. Let's try r equals 2 cosine 3 theta. Well, the first thing we're going to have to do if I'm going to use the same technique is I'm going to have to decide what the rectangular graph of this function looks like. And yeah, you could plug it into your calculator and let it do it for you, but let's do some mathematics here. So if I know what this much of the graph looks like, I'll just multiply all my y values by 2 and get my new one. So what does the graph of cosine 3 theta look like? Well, we know that the graph of cosine of a thing goes through one period as the thing goes from 0 to 2 pi. So cosine of whatever I'm covering up here, as I go from 0 to 2 pi, I'm going to go through one period. And the thing I'm covering up here is 3 theta. So as 3 theta ranges between 0 and 2 pi, I'm going to go through one period of the graph. Well, let's just divide everything through by 3. 0 divided by 3 is 0. 3 theta divided by 3 is theta. 2 pi divided by 3 is, well, 2 pi over 3. And so as theta goes through the range from 0 to 2 pi over 3, this function is going to go through one period. And I know what a period of the cosine graph looks like. Let's see. So what I'm going to do is I'm going to call this 2 pi over 3. And let's put some quarter points on here. So if this is 2 pi over 3, then halfway is, well, pi over 3. Half of this is pi over 6. And let's see, if the distance from here to here is pi over 6, then this point must be, let's see, 1 pi over 6 to 3 pi over 6. Well, 3 pi over 6 is pi over 2. And so these points mark off the quarter points, I like to call them, for the cosine graph. And this 2 tells me instead of ranging between -1 and 1, I'm going to be ranging between -2 and 2. So put a 2 up there, put a -2 down here. And then I'll just sketch a cosine graph. So in the first quarter, it's going to look like that. Second quarter, third quarter, fourth quarter. And I may need more, but we'll take care of that if I do in fact need to. And let's see what's happening. So between 0 and pi over 6, let's see, let's draw pi over 6. That's about that angle right there. So as I range from 0 to pi over 6, I'm going to be going from, well, let's see, at 0, I'm at 2 units out from the origin. So 2 units out from the origin whenever theta is 0. So that's going to be a point on my graph. And by the time I get to pi over 6, I'm going to be 0 units away from the pole. So I'm heading toward this point right there. And remember what I said, anytime we're at the pole, the ray describing the angle that we're at is going to be tangent to our graph. So I know that my graph is going to have a tangent line. This is going to be a tangent line to the graph, so I'm going to kind of sketch that there. And so let's see, as theta goes from 0 to pi over 6, my r's are ranging from 2 to 0. So this is going to get smaller, 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 smaller until I get to pi over 6. And then let's see what's going to happen. Now I'm going to head out toward pi over 3. Now let's see, pi over 3 lives right around here. But my R values are negative. So instead of sketching in this region, I'm going to be sketching in this region. So let's do that. And I'm going to be heading toward 2 units out from the pole. So 2 units out from the pole looks like this. Whenever I'm going backwards, remember this is my theta line, right, that I'm heading toward, but I'm going backwards. So I'm going to be heading back toward this direction. My R values are increasing. And I'm going to have a piece of the graph that looks a little bit like that. As I move toward pi over 2, so as I move toward theta being pi over 2, my R values are still negative. So I'm going to be graphing in this region. And by the time I get to pi over 2, I am back at the pole. So pi over 2 is going to, that ray is going to turn out to be tangent to my graph. And so let's see, my R values are decreasing, 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 decreasing until I get to 0. All right. Between pi over 2 and 2 pi over 3, I don't have to think quite as hard because my R values are going to be positive. 2 pi over 3 looks a little bit like that. And I'm going to be heading out toward 2 units from the origin, 2 units from the pole. Call it the pole in polar coordinates. So I'm going to be heading out there. I'm here right now. This line is tangent to the graph. And then, so my R values are getting larger until I get to there. Well, that doesn't quite look complete yet. Looks like I'm going to have to extend this a little bit further. So let's go another, let's see, pi over 6 is each quarter. So I'll go another pi over 6 out. This is what, 1, 2, 3, 4. So this is 5 pi over 6. And I have a feeling we'll probably have to go out another pi over 6 to pi. So let's sketch the rectangular portion first. So we have something to go off of. There we go. All right, so from 2 pi over 3 to 5 pi over 6. 5 pi over 6 is right around here. My R values are positive, and I'm heading back toward the pole. Whenever I'm at the pole, my 5 pi over 6 ray is going to be tangent to the graph. And so I'm going to wind up with something that looks a little like that. And then between 5 pi over 6 and pi, oh, my R values are negative again. So instead of sketching in here, I'm going to be sketching in here. This ray is tangent to the graph. And increase my R values until I get to 2 units away from the pole. And that looks like it gives me a complete graph. So I get this, this tripedal graph that is the graph of this polar equation. One more for good measure. Let's sketch the graph of 2 plus 2 cosine theta. Let's see, what's that going to look like? Well, I know what cosine theta looks like. And so I also know what 2 cosine theta looks like, don't I? So 2 cosine theta is going to start up here, head down to -2 down here, come back up, right? And so between 0 and 2 pi, 2 cosine theta looks like that. And this is going to bump everything up 2 units. So instead of coming down to -2, I'm going to come down to 0, and I'm going to start at 4. So that's my rectangular sketch. So let's just going to do that. So let's see, you're going to start at 4. 2 here. I'm going to put a little dashed line in here. That's where my x-axis moved whenever I shifted everything up. And so let's see, so I'm going to go from here to, see, that would be my old 0, shifted up 2 units. And here's my old -2, shifted up 2 units. Old 0, shifted up 2 units. Old 2, shifted up 2 units is here, up to 4. And so let's see, where are my quarter points? So this is 2 pi right here. Halfway through is pi. This happened at pi over 2. And this was in the point at 3 pi over 2. So there's my rectangular sketch. Let's use it to inform my polar sketch. Looks like this might be a little easier to think about. All of my r values are positive. I'm not going to have to think backwards for any points. Okay, so what do we have? At theta equals 0, again, that's this ray. At theta equals 0, my r values are 4 units out from the pole. So we'll call that 4 and put a point there. As my theta values increase, by the time I get to pi over 2, I'm 2 units out from the origin. So if this is 4, then 2 units out is right about there. And my r values are decreasing, right? They're decreasing from 4 to 2. So indicate that this way. Right? My r values are getting smaller as my thetas are getting bigger. As I go from pi over 2 to pi, my r values are decreasing to 0. So by the time I get to my theta equals pi line, I'm going to be back to the pole. And because I'm at the pole, at pi, my theta equals pi line is going to be tangent to the graph. So I'm going to indicate that. Right? And my r values are decreasing. So I'm getting closer to the pole as I move toward that point. See, my r values are getting closer and closer, or they're getting smaller and smaller as I move along. From pi to 3 pi over 2, let's see, 3 pi over 2 lives here. I'm going to be heading back out to 2 units out. So back out to 2 units out. And then from 3 pi over 2 to 2 pi, I'm heading back to 4 units out. Increase the values of my r as I move along. And I have something that looks a little like this heart on its side. Sometimes called a cardioid because of that shape. So there we have it. And that's our introduction to polar coordinates. I hope you enjoyed this video. And until we meet again, I hope you stay safe, stay well. I'll see you then.